Hello everybody. We're going to talk about equivalent expressions and solutions basically in a nutshell. So kind of previous to this, equivalent expressions are just two things that have the same value. So something like this, 9 is the same as 9. So we say these two things have the same value. So we can say 9 is equal to 9. These are equivalent expressions. This is an expression and this is an expression separated by an equal sign. Now I could break that up and I could say, well, 8 plus 1, that has a value of 9 and it's also equal to 9. So this, I think everybody understands, is that these two things have the same value. So this is what we call a true statement. It's true. If I were to say 8 plus 1 equals 7, now you say, well, these two things don't have the same value. So this is a false statement and it doesn't really make sense, right? So we would say it's not equal to. Okay. Now, it comes along that in nature and in science and everything like that, we start to have these patterns that we recognize, and we say, well, 3 times one number plus 2, that ends up being the same as 4 times that same number, but taking away 1. So that pattern that we recognize in nature, it's useful to order it in a way that is mathematical. So then we can go about manipulating this to find out what is the value that makes this always true. So we want to find out what makes it true. Okay, and it's usually the case, and it has to be the same. This one has to be the same placeholder. Like maybe early on, you had blank plus 6 equals 7. So the only thing that makes that true is, right, 1. 1 plus 6 makes that 7. So that's like a placeholder, and this is the same thing. It's just a placeholder. So I say 3 times what number plus 2 is the same as 4 plus that same number minus 1. So we can use our rules of math to solve this equation, and one of them is that property of equality. Whatever you do to one side, do to the other. So if I take away from this side 3 times whatever that number is, and I do that to both sides, so 4 times a number minus 3 times a number, well, that's just 1 times the number, right? 4 times 10 minus 3 times 10 is just 10. And you would see the same, that whatever the number is, it's always going to be just 1 times the number. So we get that number minus 1 is equal to 2. And then if I add 1 to both sides, that's a rule that I can follow. And 1 take away 1 is just 0. So I'm adding nothing to that number, and I have 3 is that number, right? So our 3 is x. So I say the value of 3 for that placeholder should make this statement true. Okay, so you can always check your answer by plugging it back in. So let's do that. 3 times 3 plus 2, this is 9 plus 2, so this is 11. And over here, 4 times 3 minus 1, yeah, 4 times 3 is 12 minus 1 is also 11. So you see that this is a true statement. And that's all we're doing when we're solving equations, is finding the value that makes a statement true. Now things get tricky when we throw parentheses around, but as long as we follow these rules of math, we can always manipulate it in a way that we can come to some solution, or say there is no solution. There are 2 basic rules for no solution. That is, we can't divide by 0, so no dividing by 0. And we can't take a square root of a negative number, at least for a real solution. So these are negative number, I don't know, something like that. Okay, we can't do those 2 things. Otherwise, there's no real solution. Okay, so what is a placeholder here that would make the statement true? Well, I know a rule that I can use to kind of make this a little simpler for me. I can use the distributive property. I go 3 times x, and 3 times that number, which is 6, is equal to 6x plus 5. And then I just move things over. I'm going to subtract 3x on both sides. And then I'm going to move that 5 over there, because I want to get the 1x by itself added to nothing. is 5, so this is 1 equals 3x, and then I divide both sides by 3, so I get x is a third. So that is the value that if I plug it into the original equation would make the statement true, and I can just check that. 3 plus, times, let's see, a third plus 2 is just 2 and a third equals 6 times a third plus 5, so this is, what is this? Well, 2 times 3 is 6, plus 1 is 7, so this is 3 times 7 thirds. Is that equal to, let's see, 6 thirds plus 5, which is just 2, right? 6 divided by 3 is just 2. 2 plus 5 is 7, and then 3 times 7 thirds is just 7. So 7 is equal to 7, so it checks out. Now I'll do this again. So 3x plus 6 is equal to 3x plus 6. Well, anybody could have told me that. I would have said, yeah, that's true. But let's go ahead and do our manipulations just like we would have done before. Let's subtract 3x from both sides. So we get 3x minus 3x, which is just 0 x's, is equal to 6. And 0x is equal to 6, so I get 6 equals 6. So this is kind of a situation where we say, oh, well, this is always going to be true. It doesn't matter what value of x I put in there, it should always work. So let's try, I don't know, x equals 5. And I have to also put x equals 5 over here. So 15 plus 6 is 21 equals 15 plus 6 is 21. So you see really x is, there's an infinite number of solutions. So I just say it's all the real numbers. Okay. So this is a situation that might come up, is you might have more than one solution, right? And now let's look at something with an inequality. So what value makes this statement true? Well, I can just guess and say, well, 0, anything times 0 is 0, so 0 plus 2 is 2. Is 2 less than 50? Yeah, so t equal to 0 is a solution. But is it the only solution, right? Let me try 1, right? So 1 times that would be that, so it's 2.54 is less than 50. Well, that's true too, so t equals 1 is also a solution. But I want to find out basically what are all the solutions, right? I don't want to just limit myself to one solution if there are more than one solution. So the way I could solve this is just like I was using my properties before. I could subtract 2 from both sides, and then I have 48. And I get 0.54t, and then I divide both sides by 0.54. And let's see, let's look at this with the calculator. 48 divided by 0.54, I get 88.8. So t is less than 88.8 continuous. So if I put in 88.8, I bet it gives me a value of 50, right? So 88.88 times 0.54, and then I add 2, so it's pretty close to 50, which I approximated it. So yeah, that's when it's equal, but anytime t is less than that value, so if I pick 80, it should be true, right? So 0.54 times 80 plus 2, yeah, that value is less than 50. So all the values that would be true would be all the values that are less than this 88.8 continuous, right? So the value itself would be equal to, though. And so the value itself is not included. So what I do is I draw an open circle and I say that value itself is not included, but everything right up to but not including that number would be true. And then everything below it would be true. So this is what we call this is the less than or strictly greater than symbol. We use an open circle. If it's also equal to, if there was a little bar under it, then I would fill that circle in and say it's also, the value itself would also be true. What else? There's also, sometimes there's two placeholders. So it's like this number is equal to 2 times some other number minus 4. Well, let's just try a value. So if this value was 0, then what would be true? Well, I get negative 4 on this side, so this would have to be negative 4, right? So this is one solution, right? X equals 0 and y equals -4. That's one solution. Is it the only solution? Well, let's try something else. What if it was 1? Then this could be, let's see, 2 minus 4 could be -2. And so this could be -2, right? So -2 equals -2. So this is another solution. X equals 1 and y is equal to -2. So that's another solution. So where are all the solutions, right? If you were to graph this in an xy plane, you would find out that they all happen to, so this point right here, x equals 0 and y equals -4, oops, down here, and x equals 1 and y equals -2 right here. And if we started plotting all these points that make it true, you'd find out that they all end up, and even if we went in between, if we put in x equals a half, for example, so x equals a half, that makes that 1, minus 4 is -3, so y would be -3. So actually it's right there, right? So you'd find out that whatever point that you put in, it all happens to end up on this line. And instead of drawing every individual point to say all these points are solutions, we just draw a line and say that whole thing represents all the solutions that make that statement true. Okay, just a couple more. So here, let's see, I'll multiply both sides by 4. That's okay, I can do the same thing to both sides. And then I get x plus 2 equals, I'll say 4/5 times x plus 2. Okay, and then I'll distribute that. So I'll say x plus 2 equals 4/5 x plus 8/5. Okay, and then subtract that over, and I get 1/5, right? Because this is 5/5 x. 1/5 x, and then I'll subtract that over, so -2 on both sides. And this is the same as 10/5, so -2/5. And then I multiply both sides by the reciprocal. I'll say times 5 on both sides. So I get x equals -2. So that's another thing. Sometimes you get a system of equations where I want this x value and some. So this placeholder plus this placeholder equals 4. Well, I could say, well, it could be 1 plus 3. That would work. Or I could say 2 plus 2. That works. Or -1 and 5 work. But this also has to be true. So the same placeholders have to subtract to equal 0. So I could think of a number, let's see, oh yeah, 2 plus 2 is 4, and also, this is minus, sorry. 2 minus 2 is also 0. So this is a solution, and if you were to graph all of these points that are true, you'd see that it makes a line. I'm not sure how it looks. Maybe it's something like this. And then if you were to graph all of these, you would see that they make a line something like that. And then where those two lines cross, so all these ordered pairs and all these ordered pairs make this line true, all these ordered pairs make this line true, and where the ordered pair that makes both of them true is at that point right there. It's called 2, 2, right? So that's just a couple examples of equation solving and how our equivalent expressions work together to help us find what makes that statement true. And you can always check that out by plugging those answers back in, seeing if it makes a statement that is true.